Hey, welcome back. Today, we're going to tackle a classic coding interview problem that's a really clever twist on a fundamental concept. It looks a little intimidating at first, but you're going to see it's built on a foundation you probably already know and love.
Okay, so let's dive right in. What's the challenge here? We're given a binary tree, and our job is to read its nodes level by level. But instead of just going left to right every single time, we're going to switch directions, creating this cool zigzag pattern.
So, take a look at this tree. How would you actually pull that off? Where do you even start? And more importantly, how do you keep track of which way you're supposed to be going on each level?
And this is our target. This is what we need to produce. Notice the pattern here. Level 1 is just 3, left to right. But then level 2 flips. It becomes 29, right to left. And then for level 3, we flip back again to 15, 7, left to right. That's the zigzag.
So here's how we're going to break it all down. First, we'll quickly review a standard traversal. Then we'll introduce the one simple twist that makes all the difference. We'll walk through our example step by step, and then we'll wrap up with performance and the key takeaways.
Okay, so before we can get all fancy and start zigzagging, we've got to make sure we know how to walk a straight line, right? So let's do a super quick refresh on a standard level order traversal, because that is the foundation for our entire solution.
And the essential tool for the job, for any level order traversal, is breadth first search, or BFS. And the heart of BFS is, of course, the queue. You know, that first in, first out data structure. It's just perfect for making sure we process one entire level of the tree before we even think about touching the next one.
It's really this simple, elegant, four-step recipe. You start by putting the root in the queue. Then you just loop. And inside that loop, you process all the nodes that are currently in the queue. That's your current level. And as you process them, you add their kids to the queue for the next round. This structure is everything. So, we have our standard traversal down. Now for the fun part. How do we tweak this to get that zigzag pattern? Well, the answer is surprisingly simple, and it's a fantastic example of how one tiny change can completely alter an algorithm's output. And this slide just lays it out so perfectly. The core mechanics of how we visit the nodes, that stays exactly the same. The only thing that changes, the only thing, is the direction we record the values in once we've processed a level. And the solution, well, it's almost laughably simple. It's just a direction flag. That's it. That's the secret sauce. The entire solution just hinges on adding one single variable to keep track of which way we're supposed to be going.
So think of this flag as our little traffic cop. It's just a Boolean. We can call it left for simplicity. It's going to tell us what to do with the values for the level we just processed. We'll just flip it back and forth after every single level. True, false, true, false. You get the idea.
All right, theory is great, but let's see this thing in action. We're going to walk through our original example tree step by step. Let's keep a close eye on our queue and, of course, that all-important direction flag. Okay, level 0. We kick things off with the root node, which is 3, so we pop it into the queue. We'll start our left flag as true. We process this level, it's just the number 3. Since left is true, we just add it to our answer as is. Boom, our result is, quote, 3. All right, now for level 1. We just processed node 3, so we add its children, 9 and 20, to the queue. And here's the key moment. After finishing level 0, we flip our left flag to false. So now, when we process this level, our temporary list of values is 9 and 20. But what do we do with it? This is where the magic happens. It comes down to one little line of logic shown here in Python. It's a simple question. Is the left flag true? If it is, append the list. But if it's not, append the reversed version of the list. And since our left flag was false, we hit that else condition. The list 920 gets flipped to 29, and we add that to our answer. See? This simple little flip is the entire heart of the zigzag. And now for the grand finale, level 2. As we processed 9 and 20, we added their children to the queue, which gives us 15 and 7. We flip our left flag back to true. So, when we process this level and get 15, 7, our flag says go left to right. We add it as is, and we're done. And just like that, we did it. We've successfully built the zigzag traversal. So let's kind of zoom out now and talk about how efficient this is and what the key ideas are that you can take with you to other problems.
So how fast is this thing? Well, it's super efficient. We touch every single node in the tree exactly one time. That's it. So the time it takes is linear, or O(n). Same goes for space. In the worst case scenario, the widest part of the tree will be sitting in our queue. So our space is also proportional to n.
You know, the big takeaway here isn't just this one solution. It's about a whole strategy, a way of thinking. You start with a simple, solid algorithm you already know, like BFS. Then you just ask, what little piece of information do I need to track to get the result I want? In this case, it was just a simple direction flag. It's a powerful technique.
And that leaves us with a really cool question to chew on, right? If one little Boolean flag can turn a straight line into a zigzag, what other kinds of state could you track? What if you tracked the depth of each level, or whether a node was a left or a right child? What other interesting patterns could you create?